Hey everyone, welcome for my lesson on finding our least or lowest common multiple. And we're going to use a different method this time. It's going to be the prime factorization method. So this way is a little bit different than our skip counting. This one really dissects our numbers, and we look at how they're formed of prime numbers multiplied together. So when we're trying to find the lowest common multiple, the first thing we have to do is we have to build our factor trees. You may remember factor trees from earlier years. We're going to build our factor trees. And I'll show you what that looks like in just a moment here. Okay, so let's start with 12. Let's build a factor tree for the number 12. Okay, so when we build a factor tree, we're essentially looking at what pairs of factors make up the number 12. So we can write these out here. We have 1 and 12. We have 2 and 6 because 2 times 6 equals 12. 1 times 12 equals 12. We also have one more set, 3 and 4. So we can go with any of these lists and to begin. Any of them except for 1. Never recommend choosing this one because if we go with that one, 1 and 12, well, we're just going to start from square one. We're going to be asking ourselves, what sets of factors do we have for 12? So never go with the factor that is the number times 1. It's never going to get you to the answer, so let's avoid that one. So I wanted to point out that you cannot use it. So I'm a very careful mathematician. I like to really take my time with my work. So when I have even numbers and I'm building a factor tree, sometimes I just like to go with 2 times whatever that second pair will be, especially if it's a really big number. You can always run some divisibility tests to see if it works with other numbers, but going with 2 is always a safe bet. It takes a little longer to get to the final answer. Small disclaimer for those who like to get straight to the point, you may want to find other factors to get you to the solution quicker. But again, I'm a very slow and careful mathematician. So I'm going to go with 2 and 6 because 2 multiplied by 6 gives me 12. That's essentially what a factor tree does. So our leaves of our factor tree, so by the leaves I mean the ends of the trees. I'm going to pull a leaf over that, or a very loopy green circle. When we have a prime number in one of our, as one of our leaves here, we know that we're done. And a prime number is a number whose factors are only 1 and themselves. So any other number, right here, prime number, any other number that doesn't fit this rule is called a composite number. So 12 is a composite number. 2, because 2's factors, 1 and 2. Those are 2's only factors, so therefore 2 is a prime number. Let's look at 6. What list of factors do we have for the number 6? We have, well, I'll write it over here, 1 and 6. Writing it out for formality, remember we don't want to go with this option because it's going to get us nowhere. We're going to get a 1 down here and a 6 down here, and we're just going to have to repeat the step. Other factors of 6, we have 2 and 3. Perfect. Let's go with 2 and 3. Those are nice numbers to work with. Okay, so we have here 2 and 3. Well, we've already determined 2 to be a prime number, so I'm going to circle that as one of my leaves. That. 3 is also a prime number. 3's factors are only 1 and 3, so we know that 3 is also a prime number. Super. Okay, so what I'm going to do is I'm going to pause here on the factor tree. I'm going to create the other factor tree for 14. I'm going to erase all my jargon over here. Okay, so let's do 14. I'll do 14 in a different color here. See this beautiful shade of blue. Okay, so 14. Let's build our factor tree for 14. Beside the number here, I'm just going to write out some paired factors here. 1 and 14, 2 and 7. It's not divisible by 3, 4, or 5, or 6, so I can just stop here at 2 and 7 because I found my last set. Excellent. So I'm not going to go with 1 and 14 because I would just be spinning my tires in the mud. Let's go with 2 and 7. Great. Well, we know that 2 is a prime number. We've determined that already. Put that little, turn it into a leaf there. What about 7? Is 7 a prime number? If you're thinking to yourself, well, I'm not really sure, Miss N, let's find out. We have 1 and 7. 7 is not divisible by 2 because we don't have a ones digit in the, an even number in the ones digit. It's not divisible by 3 because the sum of its digits is not divisible by 3. Same thing goes for 4. It's not an even number. It doesn't end in a 0 or a 5, so it's not divisible by 5. And because it didn't pass the check for 2 or 3, not divisible by 6. So 7 is also a prime number. It's handy to know which numbers, let's say maybe under 20, that are prime for these exercises. So if you build a list for yourself, that might be a handy tool to have. Okay, so our next step here is we're going to write out the prime factorization of each of these. So I'm just going to step 2, write prime factorization for both. Excellent. Okay, so for 12, what we're basically going to do is take all of our numbers that we've circled here and we're going to multiply them together. Let's see what happens. We have 2 times 2 times 3. Okay, so we have 2 times 2, which is 4, and then 4 times 3 equals 12. Hey, would you look at that? We multiply these prime numbers together. When we got to the ends of our factor tree, we end up getting a statement. This is called the prime factorization of our number 12. Awesome. Do the same thing for 14. 2 times 7. Well, that's pretty straightforward. We only have 2 here. Only one pair of factors for 14, so we end up getting 14. But you may ask yourself at this point, well, Miss N, how does that relate to least common multiple? Well, we can use this form, this prime factorization, to find similarities between our numbers. So what we need to make sure is we're going to kind of create a list down here. We need to make sure that both numbers are represented in the list in the least amount of numbers possible. So we don't want to add any extra numbers. Keep it straight to the point. So what I'm going to do is I'm going to start with 14 because it has less numbers. That's maybe a good strategy to use. So I'm going to have 2 times 7. Okay, now I'm going to look over at my 12. So we've included a 2 and a 7 in our statement down here. Pardon me, I'm just going to use a different color. It might make things a little bit clearer. I'm going to use magenta. All right, sorry about that. So you've got 2 times 7. Okay, so we need to make sure that these numbers that represent 12 are also included. We have a 2 already, so we don't need to include a second 2. We don't need to include this 2. It's already been included once. But we want to make sure that these ones are accounted for. So we can write again 2 times 3, right? We've included this number and this number's been included, and this number's been included. So now we've included at least all of the numbers in our list. Why did we not add the second 2? Or pardon me, yeah, I guess add the second 2 to the list down here. Well, if we added the second 2, we're going to be moving away from our goal of finding the least or lowest common multiple. This number here, which we're going to, first we should organize it. Let's group our 2's together, 2 times 2. Now let's put our 3 and our 7. Let's organize them in chronological order, just for organization's sake. And let's find out what this number equals. 2 times 2 is 4, times 3 is 12, 12 times 7 is 72. I hope. I just checked that very quick in my brain. Okay, I'm going to show you one more thing. I just want to point out that our 14 is represented here, and our 12 is represented here. So we can find our 12 right in here, and our 14 is with the 2 and 7. So if we included that other 2 in the mix, we would end up getting double of 72, which is 142. And that's a lot bigger than our 72. We're looking for the least common multiple. So after combining our prime factorizations, we can say that our least common multiple of 12 and 14 is going to be equal to 72. You might be asking yourself, why couldn't I have just used skip counting? Well, I guess we could have done skip counting a lot quicker, but sometimes we have numbers that are quite large. And using this prime factorization method, if you can quickly build a factor tree with some practice, it does get a little bit quicker. You might be able to find these multiples a lot more efficiently. So I'm just going to quickly show the skip counting method over here. 60, 72, 14, 28. Oh, help me out, 32, 42, 58, 72. So yeah, we could have figured out that the lowest common multiple using skip counting was 72 a lot quicker, but it's good to be familiar with this method as well. For example, this question down here, we've got the lowest common multiple of 12 and 32. These are bigger numbers, so even as you start skip counting, you're going to get to large numbers pretty fast. So I'm going to do this example a little bit quicker. If you can go back and watch the first one, that may help you out a little bit. So I'm going to find a pair of factors that go with 24. Okay, I've got my factor pairs there. 1 times 1 times 24 is 24, 2 times 12 is 24, 3 times 8 is 24, 4 times 6 is 24. Okay, so I'm going to choose, again, I said I'm a very careful mathematician. I'm just going to go with my 2 because it's familiar to me. And if you know 24 is an even number, you know that it's going to be divisible by 2. We've already done 12 up above, so I know that it breaks down into 3 and 4. So then I've got my prime number here. I've got a prime number here. I should be circling these in green. Silly me. Got my leaf right here. I've got a leaf right here. 4 is a composite number. Its factors are more than just 1 and 4. We also have 2 and 2, right? Because 2 times 2 is 4. Excellent. I'll circle my leaves down here. Okay, so what about 32? Okay, so I've got 1 and 32. Got 2 and 16. It's not divisible by 3 because it doesn't pass that test. 3 plus 2 is 5. 5 is not divisible by 3. So we know it's not divisible by 3. Is it divisible by 4? Dun, 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 dun. I think it is, right? 4 and 8, actually. There we go. That's another ordered pair. You'll notice with these factor pairs, as you get closer to the bottom, numbers get closer and closer together. So as the numbers get closer and closer together, that's another clue that you're running out of factor pairs. It's not divisible by 5 because it doesn't end in a 5 or a 0. It's not divisible by 6 because it wasn't divisible by 3. And 7's divisibility rules are not very fun. So we're gonna leave 7 out of the equation. So I'm going to go again with 2 and 16. Some of you may be eager to go with other factors as it's a lot quicker, but again, I'm just trying to show as many steps as possible for this explanation. Okay, my factors of 16, that's a perfect square. So I know that 4 times 4 is 16. We're not done. These are not prime numbers, so we have to keep breaking them down. Perfect. So we've got all of these 2's. We have all of these prime numbers. Excellent. Let's circle our leaves to say that we've finished our factor tree. Excellent. So this is our next step. This is where things get kind of strange. Might be a little bit. Oh wait, we have to write our. Excuse me. We have to write our prime factorization first. Things get strange in the next step. Okay, so we're just going to basically organize these numbers from lowest to highest. So we have 24 is equal to 2 times 2 times 2 times 3. I've included all of these numbers. I can quickly check. 2 times 2 is 4. 4 times 2 is 8. 8 times 3 equals 24. So this story checks out. Our prime factorization is correct here. Now let's go with 32. We're just going to organize them from high to low. Well, that's pretty easy. We've got 5 2's. 2 times 2 times 2 times 2. All right, so we've got 5 2's. We can do the math there. 2 times 2 is 4, times 2 is 8, times 2 is 16, times 2 is 32. Sorry if that was a little bit quick.